Well, hi everyone. In this video, my goal is going to be to give you a quick crash course on the basics of nth order linear differential equations. So these are very common equations that come up in many real-world situations, and it's going to be important for anybody studying engineering or the sciences to be able to study and solve nth order linear differential equations. On the first line of my board here, I wrote down the general form of this equation. As you can see, there are different derivatives of the unknown function y appearing in each of the terms on the left-hand side. The right-hand side has some function f of x. Keep in mind that all of the functions involving x can be any functions whatsoever. So they could involve trig functions, rational functions, logarithm functions, exponential functions, anything you might have seen in a calculus course. Everything is fair game for those functions of x, those coefficients in front of the different derivatives of y. But y is the unknown function that we're really trying to solve for. Our goal is, after all, to solve for this unknown function y. Now, one thing I like to do early on in this discussion is introduce this so-called D notation. The D that you see on the second line of my board here is really just a derivative operator. And we can think of it in this way, that if we applied D to any function f, it would simply take the derivative of that function f. So D is just simply a reminder to me that I'm going to take a derivative whenever I see it. And you'll notice that there are powers of D appearing here on the left side as well. That just reminds me that I'm going to be taking potentially higher derivatives. So for example, D squared of f would be the second derivative of f, and so on and so on. We could take any number of derivatives of f, and that could be represented as d to the k of f, and the result of that is simply the kth derivative of f. So if I take advantage of this D notation, I can rewrite my nth order linear differential equation completely in terms of D. I'm also going to suppress the x's that I wrote down on the first line. They're still there. I'm just not writing them down as I look at this D notation. So I'm just simply writing a naught times d to the n plus a1 times d to the n minus 1, and so on. All of that is compressed into a single expression that acts as an operator on the unknown function y. And notice I've kind of factored the y out over here. Every single term of this left-hand side will operate on y as we sort of expand out the left side of that differential equation. Okay. Notice that the n here is referring to the order of the differential equation. It's the most number of derivatives that we're going to see when we're looking at this particular differential equation. So that n has that particular meaning in connection with this expression. Now, we can also take this entire operator on the left-hand side and compress it down into a single operator, which we can call L. L stands for linear. It's because it is still a linear operator. And we can just really compress our differential equation so that it reads L of y equals f. No matter which way you write the differential equation, the goal is always the same thing. Let's try to solve for the unknown function y. So we're going to learn how to do that. We're going to learn how to solve this differential equation as we proceed. It turns out, though, that the first step, and really the easier thing to do, is to consider the associated homogeneous differential equation first. So let me write that down. The associated homogeneous nth order linear differential equation would simply be L of y equals 0. So if we just ignore the capital F that was originally on the right-hand side of the differential equation, and we look at this differential equation first, it turns out it's a bit easier to solve. One of the reasons that it's easier to solve is that the solutions, let's just write this here, the solutions to this form the kernel of L. If I view L as like a linear transformation, and I want to find the kernel of L, well, I would set the transformation equal to 0 and solve for which vectors, in this case, the vectors are the functions actually, which functions actually solve my differential equation. And the kernel of L, this is a very nice theorem in the theory of differential equations, is that the kernel of L, so if I'm given L of y equals 0 as above, then here's the nice result, guys. The kernel of L forms an n-dimensional vector space. It forms an n-dimensional vector space. That's super cool to know that, because that tells me how many basis vectors I would need to write down, and it tells me that every solution to my differential equation is a linear combination of that basis. Okay, so the kernel, as we probably have learned by now from a linear algebra course, the kernel of any linear transformation is always a subspace, okay? And this theorem is just telling us that it's actually going to be an n-dimensional subspace, where again, the n is just matching from the order of the differential equation, okay? So we can set our sights on trying to find a basis for the kernel of L, and that will solve our differential equation. Let me give you an example. If I had the differential equation y double prime plus y equals 0, I could rewrite this in the d notation as d squared plus 1 of y is equal to 0. And in this notation, then my L just becomes the d squared plus 1 part. This differential equation is already homogeneous. I've already got my 0 on the right-hand side. And so solving this differential equation just amounts to finding the kernel of L. And according to our theorem, that kernel will form a two-dimensional vector space. 2 because this is a second order differential equation. So n is equal to 2 for this example. And if n is equal to 2, that means I'm going to need 2 basis vectors in order to find my general solution to the differential equation. Well, what we're talking about here, guys, are functions. We're looking for 2 functions such that when I take their second derivative and add the second derivative of the function back to itself, it cancels out. And if you just think about your experience with calculus for a few minutes, you'll probably realize that there are 2 functions that are pretty well known that have that property. And one of them is the cosine of x. I'll call that y1 of x. And another one is the sine of x, and I'll call that y2 of x. These 2 functions are both going to solve this differential equation just kind of by inspection, okay? Now, a little bit later in this video, I'm going to explain how you could have come up with these functions, even if you didn't just happen to think upon it as a sort of a reflection back to calculus. Let's say that you weren't quite sure how to come up with these functions in the first place if you hadn't just noticed that they are going to be solutions. If you didn't know that kind of off the top of your head, it's actually okay. We're going to learn a systematic way to do it. But you hopefully can check if you take 2 derivatives. So if I take 2 derivatives of the cosine of x, you can check that you'll get negative of the cosine of x. And if you do the same thing with the sine of x, two derivatives of the sine of x is going to be the negative of the sine of x. So absolutely, these two functions are solutions. And notice that these two functions are linearly independent. That set of functions is linearly independent because they are not scalar multiples of each other. If you think about it, you can't just take the cosine of x and multiply it by a constant and get the sine of x. The graphs don't work that way. The functions don't work that way. So these functions are not scalar multiples of each other. There's only two of them there, so I can conclude that these functions are Li. Absolutely true. And therefore, guys, they are therefore a basis for this two-dimensional subspace. They will be a basis because there's the right number of them, and those two vectors are Li. So they have to be a basis. And so because of that, the general solution would be that every solution to my differential equation is a linear combination of these two basis solutions. So that's pretty cool that we can find all of the solutions to our differential equation just in terms of these two alone. So all of the solutions to our differential equation can be built out of cosine of x and sine of x. So it's actually pretty simple when you think about it. Okay, feel free to pause this video if you've got anything you're doubtful about, jot some notes to yourself and let me know. I'm happy to answer questions and try to clarify anything. I want to do one more example of this kernel of L idea. Let's suppose I actually give you another operator for L. Let's just take an example here. Let's do one more example. Let's let L be equal to D minus 6x. Okay? And let's just do this. Let's try to find the kernel of L. Finding the kernel of L is going to amount to solving a differential equation. And that differential equation, by the way, if we write it down, this is how you would solve for the kernel of L. You would set L of y equal to 0. And what is L of y? Well, that's D minus 6x of y equals 0. And if I expand that out, you see, this is really just a first order differential equation. It's just a first order differential equation. So here I've kind of gone in reverse. I started with the L notation, then I reflected about what the D notation would be, and then I'm actually putting it back in more of the standard derivative notation, the prime notation that you usually are familiar with from calculus. But this is the differential equation that we have. Now, it's only first order. So if you have studied first order differential equations before, you probably can solve this. And in fact, it is a first order linear differential equation. Those are often solved using integrating factors. This one actually, though, can be solved even a little bit more easily than that, because it turns out that it is actually separable. We can rewrite the y prime as dy over dx, and we can move the 6xy to the other side of the equal sign, and then it is a very simple matter to just separate the x's onto one side of the equation and the y's onto the other side of the equation. And just to remind you folks how to solve a separable differential equation, once you get it separated, you just have to integrate on both sides. So the integral of 1 over y dy would be the natural log of the absolute value of y, and the integral of 6x would be 3x squared, and I'm going to add my constant plus c on that right-hand side. Next, if we can, we should try to solve for y. I can exponentiate both sides here. And the exponentiation cancels the logarithm and leaves me with the absolute value of y, where on the other side I have e to the 3x squared. Now this plus c can be split apart, right? I can think of this as e to the c, which is really just some new constant, which I'll call c1. And it's multiplied now rather than added. So just be careful with the algebra on that. The exponent has a plus sign on it, but it splits it apart into a product of two terms. One of which is e to the 3x squared, the other of which is e to the c, but I'm relabeling e to the c as c1. Finally, I can remove my absolute value bars by allowing for a potential plus or minus sign, and I can label that plus or minus sign of c1 with c2. This would be the general solution. And this would be the kernel of L. I should point out here that the kernel of L is one-dimensional. It's one-dimensional because the order of this differential equation is first order. So it is one-dimensional, which means that the basis should have just simply one vector in it. And here it is, e to the 3x squared. Every other solution to the kernel of L is just a scalar multiple of e to the 3x squared, as you can see in the box. Okay, so this is another example of how the kernel of L can be viewed as a nice application of the vector space theory, the dimensions. So in this case, the kernel of L is a one-dimensional subspace, and we can find a basis for it, kind of like what I illustrated right there. Okay, well, this is giving us a nice way of trying to solve the homogeneous differential equation, the homogeneous nth order linear differential equation, L of y equals 0. But I do have a question that I want to make sure that everybody is comfortable with here. And that question is that we have to make sure that the functions that we are finding when we solve L of y equals 0, that those functions are linearly independent. Obviously, if I only have one vector, it will be linearly independent. If I have two vectors, as long as they're not scalar multiples of each other, like sine of x and cosine of x, those will be linearly independent. But what if I have a lot more functions than just two, right? So given n solutions, let's say y1, y2, and so on up to yn of a differential equation, how can we tell? How can we tell if that set as a whole, with all of those functions from y1 through yn, how can we tell if that set is linearly independent? Well, we have to use something a little more sophisticated now. It turns out that the answer is something called a Wronskian. This is a new concept for us. It's called a Wronskian. And let me just explain how this Wronskian is defined. This is named after a mathematician who is related to this particular theory. And essentially, the definition of this thing is that if you take the Wronskian of your functions, so y1, y2, up to yn, by definition, this is actually going to be a scalar expression. So it's going to be a determinant. And how do you fill in a matrix here using your n functions? Well, you're going to put your functions right across the first row of your matrix. So y1 through yn goes on the first row. And to build the second row of the matrix, guys, what you're going to do is just take the derivative of everything right above it in the first row. Okay? And then on the next row, you're going to take another derivative. So this now becomes the second derivative of all of these functions laid out across that whole third row. And you just keep going, taking more and more derivatives as you go down the matrix until you get to a point where the matrix will be a square size matrix. Remember, you cannot take a determinant until the matrix is square size. So on the last row, turns out you'll have to take n minus 1 derivatives of y1, and then n minus 1 derivatives of y2, and so on, all the way across. You're taking n minus 1 derivatives of everything. Okay. Normally, n will be, if you're doing it by hand, n is likely to be 2 or 3. It's not going to be a huge number. So you're probably looking at a 2 by 2 or a 3 by 3 determinant here, most likely, most of the time. But this is not a matrix of numbers. This is a matrix of functions that you have here. And so you are going to have to take this determinant. However, the real theorem here, and I'm going to call this the W test. I think this is a good way to abbreviate this. The Wronskian test is actually the following. If there is a value of x, so x is, of course, the variable that all of our functions depend on. But let's say there's some specific value of x, I'll call it x naught, such that when I take the Wronskian of y1, y2, and so on up to yn, and I evaluate it at x naught. So this just means I'm plugging that number, x naught, in everywhere into the matrix where I see x's, right? So those x's will be permeated all the way through that matrix in many, many places. I'm going to plug in a specific number for those x's, and if there is such a number that makes this Wronskian not come out to 0, if it does not come out to 0, then your original functions, y1, y2, and so on, up to yn, that set of functions is Li. Right. So your functions would be Li as long as you can find even one number that makes that Wronskian come out not 0. Okay? Maybe I should do a quick example of that Wronskian test, just to make sure that everyone is feeling okay with this. In fact, maybe we ought to do a couple examples. I'll just do one that's really fast. So, for example, going back to the cosine and the sine. Now, this one, we already know that those two functions are Li just because they're not scalar multiples of each other. But just to do the little Wronskian test on it, if I put cosine of x and sine of x into my Wronskian notation here, I'm going to be viewing this as the determinant of, in this case, a 2 by 2 matrix. So remember how this works. I'm going to lay the functions into the first row of this matrix. So y1 and y2 are the cosine of x and the sine of x, respectively. So I'm just going to put cosine of x here, sine of x here, and then the derivatives of those get laid out like that. So you're just taking the derivative of cosine and the derivative of sine. It gives you a little 2 by 2 determinant. Now, this isn't too bad to just evaluate the 2 by 2 determinant, but sometimes it could be messier than this. And so what I'm going to recommend is that before you actually evaluate the determinant in terms of x, that you actually try a value. I'm going to call it x naught. I'm going to try a number for x naught. Let's say we try to plug in 0. Okay, so that would just mean, and by the way, this is just kind of a wild guess, right? This theorem says that there has to exist there exists a value, say x naught, but we don't know what x naught is supposed to be. Hopefully the x naught can be chosen by us to be a really simple number. So 0 is always my first choice because plugging 0 into functions like this is usually pretty easy, right? Cosine of 0 is 1, sine of 0 is 0, sine of 0 is 0, cosine of 0 is 1. And now you just have to take this determinant. Obviously, this determinant is just 1. The point is it's not 0. It's not 0. And so that's what this W test says, is that as long as you can find a number to plug in for x throughout your matrix that gives you a non-zero Wronskian, then your functions are Li. So this implies that the cosine of x and the sine of x is Li. Absolutely true. Okay? Let me just do one more example, and then I think we'll be good. I want to do one that's maybe a little, just one step more complicated. Nothing too crazy, though. So here's another example. Let's show that the set of 1 over x and 1 over x squared and 1 over x cubed is Li. Let's see if we could show this. All right. So again, these are your functions, y1, y2, and y3. And this time, because there's 3 functions here, I'm not allowed to just say that they are not scalar multiples of each other, and therefore they're Li. Remember that when you have 3 or more vectors, right, simply mentioning that they're not scalar multiples is not adequate to convince me that they have to be Li. So we really do need our W test on this particular example. Okay, so let's see if we can do that. Let's try to set up the Wronskian. I'll just abbreviate it as W at this point. So the Wronskian, which is W, is going to be a determinant. This time it's going to be a 3 by 3 determinant. And remember, we're just going to lay our functions into the first row of the matrix as is. 1 over x squared, 1 over x cubed. And then I'm going to take derivatives down the matrix. So the derivative of 1 over x, by using the power rule, it would be negative of 1 over x squared. And then the derivative of 1 over x squared would be negative 2 over x cubed. And the derivative of 1 over x cubed would be negative 3 over x to the 4th. Make sure you can do these derivatives, guys. This is just the power rule. This is not anything real high-powered here. It's a pretty simple set of functions to differentiate. That's kind of why I chose it, right? So you've got to be able to do that. If I do one more derivative, see, this is not a square matrix yet. I've got to do one more derivative here. So if I do one more derivative in the first column, I'll have 2 over x cubed, right? And if I do the same thing in the second column, it will be 6 over x to the 4th. And finally, the last one is 12 over x to the 5th. So it's going to look like that. And now you can really begin to see why you wouldn't really want to have to deal with calculating this determinant with all these x's everywhere in the matrix. There's not a 0 anywhere to be seen. So it's a little bit annoying. So what I'm going to recommend is that we try to plug in a number for x naught first, and then see how it goes. Now, in this case, I cannot plug in 0 for x naught because the x's are in the denominators here, and so it would not make sense to do that. So maybe the next easiest number that I can think of might be 1. So we could try that. If I plug in a 1 everywhere that I see an x in this matrix, the first row will just become 1, 1, 1. The second row will become negative 1, negative 2, negative 3. And the third row would become 2, 6, and 12. At least now it's a 3 by 3 matrix of numbers. And to evaluate this, I probably would recommend using the arrow method. It's not too difficult to use the arrow method on a 3 by 3 determinant. So going through my arrows, I would have the first arrow gives me negative 24. The next one gives me negative 6. The next one also gives me negative 6. And then I have to subtract arrows going this way. So I subtract negative 4. Then I subtract negative 18. And then I subtract negative 12. Right? So we figure out what all of this adds up to. Right? So these numbers over here actually end up becoming positives. So 12, 18, and 4 is actually 34. And then I'm actually subtracting 36 from that in the front. So this turns out to be negative 2, which is not 0. So it is not 0. And because it's not 0, then our Wronskian test tells us that those functions are Li. You might wonder, well, what would have happened if this was equal to 0 over here? Well, if you've plugged in a value of x and you happen to get 0 at the bottom, that doesn't necessarily mean that the functions are not Li. It could just be that the x naught that you picked just doesn't work. And in that case, you might have to just try a different value of x naught and see if that one gives you a non-zero Wronskian. See, you just have to find a value. You don't have to make it always be true. Just for at least one value of x naught, I need this Wronskian to be non-zero. So that's the idea. Here, I got it on the first guess, right? I'm just trying to say that sometimes you might have to try 2 or 3 or 4 values of x naught. Now, if you try over and over and over again, and you keep failing to come up with an x naught, then it might be time to start realizing that your functions are actually LD. So if you do 2 or 3 or 4 of these and you can't seem to get a non-zero Wronskian, then it might be a good idea to stop and make sure that you really are comfortable that you have linearly independent vectors in front of you. Okay, because it might not be the case. Okay, well, this is kind of an introduction to how we approach nth order linear differential equations. Specifically, we're trying to solve the associated homogeneous differential equation that has this form. The solutions to this forms the kernel of L, which is an n-dimensional vector space. So in the next video, I'm actually going to show you how to come up with n solutions to this nth order associated homogeneous linear differential equation that you can then use to build the general solution in a specific case, right? Turns out it's an extremely common case, but I will finally give you a differential equation that we can solve that's higher order. It could be nth order, not just first order. I know we did an example of a first order equation a few minutes ago. I want to tackle any nth order equation of a certain type and give you a recipe for how to find its solutions. So that's coming up in the next little bit that I'm going to share with you right after I take a short break. Thanks so much for watching this one, guys, and jot down any questions and let me know if I can help. Thanks so much. Bye for now.